Hello and welcome to the presentation about the inclined plane. Just as a warm-up, and make sure that you've got some of the requisite knowledge required to access this information, have a go at looking at these vectors and seeing which picture is the odd one out. So we have two vectors added together and they're saying that it will add up to this red one. So just have a look and see if you can work it out. Maybe pause the video. Okay, so if you've had a look, hopefully mentally you're able to do something like this. Okay? Take the vectors, add them tail to tip, so here's the tail of this vector, I'll put it on the tip of this vector, the purple one, and the purple and the blue one have added up to the red vector. Okay, similarly the same thing for this. If I take this one and put it there, I still get the sum being the red vector. Okay, if you actually notice, the purple here and here are identical, and the blue here and here are identical. It doesn't matter what order you add up the vectors, as you see. It was blue plus purple, and this time it's purple plus blue. It doesn't matter the order, you still get the same result. Okay, down here we had slightly different sizes. Down here we have slightly different sizes, and we can still see that they still add up to the red one. In this case, though, if you can do it in your head before you see it, that helps. You can see that we've got a little bit left over. It doesn't quite add up, so this is the odd one out. Okay, the correct answer to the sum of the blue and the purple vector would have been this red one here we've just drawn in. Okay, so this is all about the inclined plane, and the aim of this presentation is so that you'll be able to visualize the components of a force and to be able to analyze the forces acting on an inclined plane. Right, so what we're going to do is look at three cases that shed some light on the inclined plane. Firstly, a perfectly horizontal plane, okay, and let's look at the weight of this car due to gravity and where it's acting from. So let's say we draw the red arrow on from the center of mass of the car, and it would just be straight down with the magnitude of the weight of the car, mg. Okay, let's have a look at a slope. On a slope, I don't think you'd be surprised that mg is still going to act perfectly downwards, and the magnitude would be the same. Okay, now let's have a look at vertically. So now mg is still acting completely down. So in all cases, mg was the same. So if we was to just draw the weight on each of these three cases on a horizontal plane, a plane at 45 degrees, and vertical, mg, the magnitude and direction is all the same. Now let's have a look at another one of the forces we're interested in. Okay, one of the components of mg. The component of mg that acts along or acts parallel to the inclined plane. So when the plane is horizontal, there's no force. This guy doesn't have to apply any force to stop this car from rolling away. Okay? When the car is on this 45-degree slope, now he's got to pull quite hard to be able to stop this, the component of gravity that's acting down the plane, pulling the car off. Okay? And when it's on a vertical, he's got to be super strong to be able to hold it. That's the most difficult scenario for this guy. So let's look at that in terms of forces. So the force is parallel to the inclined plane. When it's horizontal, no force, nothing. Okay? You don't draw a dot when there's no force. I've just put a dot there to make it visually, you understand what I'm talking about. Okay, now we're on a 45-degree plane. The component of this red arrow acting down the plane is a bit bigger. Okay? And then finally you get to when it's completely vertical, and the component is exactly equal to the magnitude of the gravity. So you can get rid of gravity and just replace it with the purple arrow. Okay, so we start with no force parallel to the plane. It gets larger, and then it's at its largest. Alright, now let's look at another force. Okay, so now we're looking at forces perpendicular to the plane. So right now, perpendicular means if you've got a plane, you draw a line 90 degrees to it, down this way. Okay, so now you've got this guy underneath here, okay, and he's holding the car up. And right now, he's being crushed. He's in pain. It's a lot of force. Okay, if we put him on a 45-degree plane, I think you can imagine that the force is going to be less now. The force of the car pushing on him isn't going to be as bad. It's like someone leaning on you or something. It's not. It still would be a lot of force, and it would probably hurt him, but it wouldn't be as bad. Okay, and if we have the force, if we have the plane vertical, there's no force. Okay, so we can now add those perpendicular forces to our diagrams. Okay, so perpendicular to the plane, okay, we'd have a force which would be equal to gravity. In this case, the car just crushing the guy. So we can get rid of the gravity, as in previously. This time it's going to be, again, perpendicular, and in this case there would be none. So I've just put the dot just to show there would be nothing there. Okay, so we've seen all the forces involved now. Now we want to see how we can find useful information about it. Okay, so, well, I'll just go back a second. If we look at this red arrow here, I hope you can see that if we took this purple line and this blue line, and we took him and we shifted him down here, you could see that it would add up to the red line. If you summed the purple and the blue line, you'd get the red line. Okay, and that's how this whole thing works. All right, so
let's take a look at the gravitational force. So here's the gravitational force. Remember, it's straight down to the center of the Earth. And there's also two components. There's the perpendicular force and the parallel. And here's the symbols for parallel and perpendicular. Notice the parallel symbol actually has two parallel lines, and the perpendicular component has two perpendicular lines for the subscripts. So this represents the gravitational force and its two components. Now notice the angle of the incline. It matches the angle inside of this triangle. Now, I want to prove this to you, make sure that you understand how it works. So here's another picture, but I've just made it a little bit more accurate. I'm going to take this triangle and I'm going to flip it, then I'm going to turn it around, and I want you to notice how the two triangles fit together perfectly. They're similar triangles. So this is the geometric proof. It's actually called law of parallel lines and law of perpendicular lines. It shows you that those two are similar triangles. So we go back, and I can pull out the parallel component and actually move it so that it's in line with the inclined plane. And we'll label it there. That's actually the gravitational component that's actually pulling the car down the hill. Now, what's opposite the perpendicular component? Well, we learned in class yesterday that is the normal force. Normal is, in this case, perpendicular to the perpendicular component of gravity. And of course, there's also the applied force, or F sub A.
Push it up the inclined plane. Push it up the inclined plane. At first they tried to lift the stones, but they got aches and cramps. They figured out it's easier to use a system of ramps. They made a smooth surface, and yeah, that does the trick. That's how they built a pyramid, pretty darn quick. Push it up the inclined plane. Whoever thought of that was really using their brain. If you want to build a pyramid, do what the Egyptians did. Push it up the inclined plane. Push it up the inclined plane.
Ramps make things easier to lift. Watch this. If I try to pick this book straight up, watch what happens. I made this ramp out of an old bookshelf and a couple of phone books. If I pull this book straight up the ramp, the string is strong enough and it takes a lot less force. The force we need to pull the book up the ramp is smaller than the force we need to pull it straight up. Cool!